Hello, everyone. Thank you for being here. My name is Vijay Samuel, and I'm the observability architect for eBay. Today, we are going to talk about how to take Prometheus planet scale. This is a talk about our journey in running a massively large-scale installation of our metrics platform at eBay. So we initially talk about how we do observability at eBay, where this problem statement began, how we went about solving it, some of the lessons we learned along the way, what we are thinking about right now, and if there's time, we can do some questions. Observability at eBay. The observability journey, as in most companies, starts with instrumentation. Developers, through the use of open source libraries that are shipped along with our managed frameworks. So these frameworks are used by every eBay developer as they come with pre-bundled utilities like tracking, observability, and any other things that is commonly required by every developer to build applications that power the eBay site. So they use the open source libraries like Prometheus client, OpenTelemetry client, and they instrument metrics logs and traces. Once instrumentation is done, they come to our eBay Cloud Console, and they do some onboarding, saying that I have this Prometheus endpoint here. Please onboard it into the metrics platform. And then a series of control loops kick in, delivering annotations to all the pod specs to make sure that we are able to find what is required by the collector to start shipping the data. So the next one is harvesting. We run OpenTelemetry collector across all our Kubernetes nodes in our eBay data center so that they can harvest the metrics and then ingest it into what we call Sherlock.io, which is our internal observability platform. Once the data is harvested, it's available for users to do alerting. If they want to do rollups, they can do recording rules. And all of this is facilitated, again, through the Cloud Console, where they can do the required onboarding of that. Alerts can either be threshold-based, or they can be based on some pre-canned models that we have to support anomaly detection. And the obvious, they can use the console to come in, build dashboards, and anything that they might find to useful to do active triage. The scale at which we run, we have, at any given point in time, 1.25 million Prometheus endpoints that are being scraped. We ingest around 41 million time series per second that's being ingested into the platform. 2 billion active time series that is stored. Roughly 8,000 queries per second, serving all the recording rules and alerts that are there. And we provide 1 year worth of raw metric retention for every tenant that's ingesting metrics. So where did it all begin? The year 2018, and cloud native is catching up inside of eBay, which means we have quite a few Kubernetes clusters that are running. There are a lot of teams actively using it. And Prometheus also is very popular by now, to the point where individual teams, instead of using the centralized observability platform at the time, they were more comfortable running Prometheus instances on their particular namespaces to do monitoring, scrape the endpoints that are there, build dashboards, and use the Prometheus Alert Manager to do alerting. And we also had the goal of trying to scale out our observability platform. The legacy system that we had at that time was a modified version of OpenTSDB, and there were a lot of problems associated with it, primarily because it was a modified version in terms of DR inefficiencies, issues with data consistency. We had a custom protocol that every application owner needed to know in order to be able to send data in. And HBase had scaling issues, availability challenges, and it was just a lot of tribal knowledge to know. A user cannot just come into the company, say I know Prometheus, and then just get going. There was a lot to learn. So what we wanted at that time was a system that scaled a lot better. It was more community-focused, richer ad hoc query support, and it should just be cloud native, meaning it should also support cloud-native monitoring out of the box. So Prometheus, something that we are well aware of, is an open source CNCF-backed time series database. It offers PromQL as a query language, which is more or less a de facto standard at this point in time. It is simple to operate because it's a single server, doesn't try to solve sharding, replication, and whatnot. It offers instrumentation clients for various languages like Java, Golang, and whatnot. It has a standard exposition format, which is easy to consume, either through libraries that they have, or you could even just write it in a matter of minutes to parse the endpoint out. And it has a very effective storage engine, which uses delta-delta encoding. So what were the challenges with adopting stock Prometheus at that time? First and foremost, there was no support for HTTP push. Prometheus does support it right now, but at that time, it was that you need to use the Prometheus scrape manager and have a Prometheus endpoint exposed so that the scrape manager, either through static configuration or service discovery, locate the endpoint and then start scraping it every so often. But for us, given that our objective was not only to cater to the cloud-native applications, but also to move over the legacy applications into the new world, we needed a mechanism in which we should be able to send metrics into the TSDB as well. So the other problem with the running stock Prometheus, the usage was typically around you run one Prometheus instance per namespace or a handful per cluster. You do either prom-fed or you use so you use prom-fed to expose a rolled up set of metrics as federation. But if you are thinking in terms of having hundreds of Prometheus instances, just managing all of this can become very tedious. And scaling is hard. Given it's a single server, you only need to be able to vertically scale up. There are users that have Prometheus instances with a terabyte worth of memory, is what I've heard. Or you basically manually shard, saying that for these set of endpoints, I'll have one Prometheus instance, so on and so forth, which also becomes very operationally challenging. So our initial goals were this, to keep it very simple. We did not want to solve replication. Instead, we'll do something like fan-out writes. And the way that we compensate is at the query time, you do deduplication. And the other goal was to use the Prometheus TSDB as is. So maybe take the TSDB, build HTTP APIs on top of it, and then allow APIs to write into it. We wanted to support simple tenanting. So have a concept of what is called a namespace, and every user is given a namespace into which they can write time series in and have some basic form of cardinality rate limiting, saying that every user for free, they get, say, 500,000 time series per metric name for free, or 20 million time series across the entire tenant. We wanted to be able to tightly integrate with Kubernetes, so the idea was to come up with an operator, have a CRD, that can realize what are called metric store clusters. We wanted to support PromQL and Grafana out of the box because that was more or less the standard at the time, and for the most part, most people continue to use PromQL and Grafana today. We want to be able to support alerting and recording rules so that people are able to know when something is going wrong, route the alert to, say, Slack, PagerDuty, email, or whatever, or even write their own webhook, which can facilitate some closed-loop remediation. Also be able to record. If they have data that is of fairly high cardinality, they should be able to roll it up so that they are able to query across days, weeks, months, or even for a year. And finally, the original goal was to support twice the cardinality limits of the legacy platform. If my memory serves me correctly, it was around 200 million active time series at that point. So our goal was only to get to maybe 400 million. And like, we were surprised with the outcome after this entire exercise. So we did a first pass. which was to come up with centralized uh, metric store or Prometheus TSDB clusters. So if you have a couple of Kubernetes clusters on which the metric store platform was deployed, what you would see is that there would be an ingress or ingest endpoint, which basically writes into ingest pods within those Kubernetes clusters. And these metric store replicas or these TSDB pods that were running will have data replicated into them at the time of ingest, or replicated is the wrong word, but fan out right. On a best effort, these ingest pods fan out right into all the replicas that are there. And when an egress or a query endpoint tries to serve a query, what is going to happen is that the reverse is going to happen. It's going to query the replicas where it thinks that the data is available. It would dedupe, pass the data into the PromQL engine, evaluate the result, and then return it back. So from a storage discovery and management perspective, we had what is called a metric store controller. This controller is nothing but an operator that can realize a custom resource definition that basically says that create a Prometheus cluster for me. So when you create a Prometheus cluster, it needs to know the number of shards that are going to be there. So what ends up happening is that it creates a stateful set with, say, 10 replicas, or 10 shards, 15 shards, 20 shards, whatever. And the CRD also has the list of tenants that have the data written into it. So I can have tenant 1 that goes into cluster 1, tenant 2 and 3 that goes into cluster 2, so on and so forth. So what's going to happen is that the ingest and the query pods, they first read the CRD and identify, tell me which cluster maps to which tenant. And when a time series comes in at the time of write, we find out the tenant ID on the time series, find out which cluster it maps to, find out what sharding technique to use, either hash all the labels, do a modulus by the total number of pods that are there, find the entry, and then write into it. So that's how we basically divvy up the data into each and every shard in a given cluster. And the reverse basically happens at the time of query, where you look at the query, the tenant is a mandatory parameter that's there. So with the tenant, you can find out which cluster to look at, read all the shards, get all the data, apply it with the PromQL engine, and then serve the data back. So all that needs to happen is that every ingest and query pods need to connect with every Kubernetes cluster that the metric store pods are deployed against. So this allowed us to get to a reasonable scale, but there are challenges still in this approach. Our data growth was almost 100% year over year, for many years, in fact. So we moved from 2 million to 4 million, 8, 16, 24, and currently we are at 40 million time series that are being ingested every second. Like I told you, the namespace is a mandatory label. So every query needs to have it, which means that it is difficult for us to support things like a labels API, where if I just say pod equal to, I cannot find out what are all the pods that are there in all the TSDB shards, because I first need to tell what is the namespace that I want to look at. So this was problematic in the sense that when people try to use autocomplete on something like Grafana, they wouldn't be able to effectively make use of it. Even though we are spreading out the cardinality into multiple shards, and we can create individual clusters for various tenants that are there, if a tenant grew large enough, the query performance starts to degrade, because the only way in which we are solving the cardinality problem is by creating more shards. And when you move from 10 to 20 to 30 shards, you still have to fan out into all of them, get all the data, apply it against PromQL and whatnot. And given that the PromQL engine currently is single-threaded, there's only so much cardinality that you can actually absorb in a single query. So if a use case is larger than a certain limit, then basically we have to have the conversation around, hey, can you cut down the cardinality because your experience is going to be very bad. And this model has a lot of dependencies that are involved. So for DR, if there are multiple regions, we house the the metric stores in various regions. So this means that there are cross-region networks that are involved, talking to the various components. There are load balancers that are involved. All of these become dependencies when you're trying to do monitoring. And for very critical use cases, you need to be able to minimize the amount of dependencies that you have to be able to effectively communicate that, hey, something is wrong with your system. So between the time from the first implementation to what we are at right now, we also did some minor enhancements. And one of that was to introduce something called as an aggregator. So if there are observability practitioners here, we all would be able to agree with the fact that raw labels aren't always required. And most of the time, if you look at query logs for the last 1 year, the amount of raw data that people actually ask for is very minimal. So if there is a use case that has absurdly high cardinality, one of the recommendations that we give to the end user is that maybe put this data through the aggregator, so that you drop some labels that have high cardinality before it hits storage. A good example for this is container ID. So every time a container restarts, even though the pod name remains the same, the container ID is going to churn each time. While it might be useful to look at logs on a per container ID basis, sticking them into something like Prometheus is a recipe for disaster, especially if it's going through a crash loop backoff. And Prometheus itself, the way that the head block is designed, each unique series has a cost associated with it, which means that the greater the cardinality, the amount of memory that you're going to spend on the head block is pretty high. And by writing or by implementing such an aggregation component, the savings that we saw was massive, in the sense that we got 60% CPU and 80% memory savings compared to trying to do the same thing with the recording rule on top of Prometheus. So what I mean is that the cost to aggregate before putting the data into Prometheus is 60 to 60% cheaper than storing it in the head block and then applying a recording rule on top of it. So this is how it would work. So the raw series is ingested into our ingester component. Then we basically apply a policy. If the policy does not match to any aggregation rule, the data directly lands on the TSDB. Otherwise, the data first goes into the aggregator, gets aggregated, and then only the aggregated time series is written into the TSDB. So at this point, we were like, OK, let's take this whole thing planet scale. So a few years ago, Google published a white paper about Monarch, what it dubs its planet scale time series database. And like every curious engineer, me and our lead engineer, Nick Prodash, we basically started to think, is it even possible to replicate such a setup inside of eBay? And what we did is a hackathon 3 years ago. Myself, Nick, our metrics track lead engineer, Sandeep, and 2 engineers, Karthik and Freesia, we had a hack week inside of eBay where you're given like 5 days to come up with something cool. And we said, OK, within 5 days, let's mock up this entire thing. And at the end of the 5th day, we had a prototype where on our data centers in the US and some of our POP locations across the globe, we had independent installations of our metric store that could do short circuit monitoring on those locations, but also have a federated view that can fan out and get data from each of those locations up and running. So that basically told us, OK, this is possible. And from that point on, we figured out how to get it productionalized. So stating the obvious, we don't have the same awesome tech that Google has. So we had to do a lot of substitutions. And those substitutions were primarily made through the usage of open source technology. We realized very early on that none of this can happen without GitOps, because managing configurations for these many independent installations is going to be really hard. Until this point, our installation was only limited to maybe 3 or 4 Kubernetes clusters, but this would take it to as many as 100. So something like GitOps is required, where we can manage everything on a Git repository, and then some automation comes in, and then it delivers it into every Kubernetes cluster that is part of this installation. And the white paper is all that we had to go with. And some of the aspects that we would have loved to understand weren't really part of the white paper. So let's understand the anatomy of what a planet scale installation should be. The raw data is closer to the source. So the time series database needs to be deployed on a per region AZ Kubernetes cluster basis, and the number of tiers is composable. So you can initially start with a single tier where a single cluster is able to manage everything. And if the scale is a bit higher than that, you can go say, okay, I will have one cluster per region. And if it's higher than that, you can say, I'll have all the raw data on every Kubernetes cluster, roll up some of it, and have it as part of a region local cluster, so that when a query comes, I can just fan out to all of them. So depending on the complexity that you need to introduce, based on how much data you're looking at, you can compose it. So rollups get bubbled up. So the leaf is where the raw cardinality sits. Everything rolled up to a certain degree sits at a zone, and even higher level of rollups sit at what is the root. So leaf, zone, and root are nomenclature that you can read about in the Monarch paper. Queries need to be federated. So it doesn't matter if you have 100 or 1,000 independent installations. What you need to provide to the end user is a single endpoint where they can fire all their queries, but the queries need to route themselves to the appropriate place. So the naive way of doing it is to know all the 100 clusters where your installation is and keep fanning out to all 100 of them. But that would be a recipe for disaster. So what the paper talks about is having something called as a field hint index. So the field hint index, in a very naive way, is nothing but a bunch of Bloom filters that might exist, saying that on this cluster, pod equal to A exists. On this cluster, pod equal to B exists. And if you keep merging that information up into the higher level, you can basically ask at the topmost level, saying that, tell me which zone does pod equal to A exist. You go there, and then again tell me what leaf does pod equal to A exist, and you can go there. So rather than going to all 100 places, you just go to the exact place where the time series is located. And as I mentioned earlier, we would have to manage everything through GitOps. So this is how the deployment architecture would look like. So you would have a leaf installation where you have the entire metric store platform being deployed. So you would have your ingester, the TSDB where it writes to, the querier where the data is read from, and an indexer which manages all the hints that are available for that cluster, and the hints are derived from the TSDB. So the easiest way to do that would probably be to have hook into the series lifecycle callback, where you say that every time a new series is seen, take all the labels and basically apply your algorithm to generate the index hints. You'd have the ruler, which is used for doing the recording rules, the alerter to do the alerting, and also an object store where you do the long-term store. In this case, this is nothing but Thanos. Oops. Wrong button. So you can have a very similar setup on the zone as well, which is meant for only storing the higher level rollups. At this point in time, the leaf and zone are just two independent entities that are there. They know nothing of each other until the point where the leaf starts to propagate its indices into the zone. So once this happens, this becomes possible. The zone can now push down queries into the leaf. So now you can keep stacking. on top of it. So this would be a root. But if you want to go 4, 5, 6, 7, 8 levels, this is how you would basically achieve it. So a query can start from the root and then go to the zone and then go to the leaf. Okay, so ingest routing. So all the scrapers exist on the leaf. They do the, we have our own control loop that Lolita alluded to in the previous talk, where a control loop figures out what needs to be scraped. We have a bunch of scrapers that are there into which the control loop pushes the configuration, and the actual scraping happens and basically writes into the leaf level. And you can have recording rules that are very specific to the zone, saying, okay, if the zone is the region, you can say, take this metric and roll it up at per zone basis. Those would basically go into the ingester and then get written into the TSDBs. And similarly, give me a roll-up that is across all zones. And that would basically go into your root. Or if there is a use case that has no concept of a region, like a specific business metric that you're deriving from a database, that could directly maybe ingested into the root itself, because the concept of a zone and a leaf may not necessarily apply there. And so we already talked about the path on the left side, where whenever a new series appears, the leaf has all the hints that are required. And from there, it gets propagated to the zone. And from there, it gets propagated to the root. So when a query comes in, what first happens is that the querier looks at the roots index to figure out which zones have the data, passes it into the corresponding zone, and the zone looks at which leaves have the data, passes the query to the leaf. The leaf looks at the index to figure out exact TSDB shards that have the data. There can be 100 shards, but only one shard that has the data. And that is returned by the leaf indexer, and then it actually makes the respective query that is required. And this also allows us to do the next aspect, which is query pushdown. And this basically solves the problem that I was talking about, where you can't keep widening the size of the TSDB cluster, and Prometheus, being single-threaded, cannot process too many things at the same time, too many series at the same time. So when a query like this comes, give me the 90th percentile of HCD request duration latency that's there. So when you look at this query, it is relatively straightforward to know that the histogram query you cannot directly push down, but the sum over the rate is something that you can push down. So what would happen is that this gets pushed down into the querier, and the querier on the zones, and the zone knows exactly which leaves it needs to push down the same query into. They ask the TSDB what are the series that are associated with it, do the roll-up, and then pass the roll-up, not the raw series. They pass the roll-up into the zone queriers. The zone queriers pass it to the root, where it is then again aggregated, and then the histogram gets applied on top of it. So this not only means that you're pushing lesser amount of data back up the stack, but also you are divvying up the problem into much more manageable chunks, rather than how we are conventionally used to doing with the Prometheus. So what did we get out of all of this? The first and most important one was that we are able to scale to much higher cardinality requirements. So right now, we run just the zone and the root, because we don't feel the need to add that complexity in right now. But we also have the capability now to say that, okay, if there is an absurdly large use case that is there, we can always create leaves for that use case. We have better ingest and query performance. So what we ended up doing as part of this exercise is that we did not use the Prometheus remote write and remote read protocol between the zones and the leaves. We wrote our own gRPC-based API, which is a lot more cheaper on the network. So one of the things that folks might have noticed is that labels are very repetitive, and regardless of compression or whatnot, like it will still take a huge chunk of bandwidth. So one of the things that we did was we created a symbol table per gRPC request, and the symbol table basically helped cut down the amount of data that is being sent over the wire. The other aspect that helps is query pushdown and query projection. So only the root, what the root will only see is rolled up data with only the required labels that it needs to see. Everything else gets dropped in the lower layers. We have independently usable metric stores. So as you had seen in the architecture, the leaf is its own independent entity, meaning that you can do a lot of short circuit monitoring within the Kubernetes cluster itself. You don't need to go through the network. And you can also set up alerts, and you can even build dashboards that are independent to the centralized entity. So an outage in the root does not necessarily prevent you from observing what is going on the zone or the leaf. And during this whole exercise, we stopped the notion of, okay, a use case is very big, create a cluster for it that has more CPUs or more memory associated with it. We moved to just a fixed sizing, saying that every shard will have the same amount of CPU and memory, which makes things extremely easy to operate. What are the lessons we learned out of this? So independently usable metric stores, like each leaf and zone is now a fully functional metric store, and that helps it be easier to visualize, and we can alert on top of it as well. GitOps makes life very easy. While it's very convenient to have your own YAML specs, do kubectl apply and whatnot, and the API server can be a record for all your specs, it is still very easy to lose them at times. So having GitOps make sure that a spec is never lost. GitOps ensures that all your spec changes are reviewed. It's easy to roll back because underneath you're relying just on the awesomeness of Git. And without GitOps, we would not have been able to even get off the ground with this installation because the operational cost to manage everything would be extremely high. Internal APIs aren't a bad thing. Like I mentioned, like when we moved to the gRPC API, the cost was massive. The initial mindset that we had was always to stick to remote read and remote write between everything. By moving to this model, it also enabled us to do query pushdown and projection. So the wins were definitely worth coming up with an internal contract that made sense for the product that we were building. And the last one is continuous observation and evolution is key. It is always good to learn new tricks along the way. So we learned something new from the white paper that we read. We were able to apply it, and sometimes that rewrite that we shy away from is probably necessary. So with this effort that we went through, we rewrote almost everything. But the reward that came out of it was definitely substantial. So what's next? One of the things that we are actively thinking about is to introduce the concept of automatic rollups. So right now, what happens is when data moves from the leaf to the zone, you need to set up your own recording rules to do the rollup. And I mentioned earlier that the raw data is rarely ever queried. So can we automate this entire process to say that if everything that is being seen in the leaf, just drop things like pod, node, and then create a metric for it on the zone, and then cut down the raw retention. And the queries can be intelligent enough to say that if it is seeing a pod or a node, it should go to the leaf, or it can just stop the query at the zone and then just work on the data that is rolled up already, which can be substantially cheaper when you're doing queries. So support of native histograms. Native histograms is something that the Prometheus community has just come out with. But this is something that we haven't fully thought through yet, like how would the query pushdown mechanism that we have work with native histograms, and even how much cardinality we would save by converting most of our regular histograms into native histograms. And the last, should we open source it? If you think that what we have built is something that might be interesting, then maybe let's talk about it after this talk. I'll stop here, and any questions? Thank you. I think there's a mic.
Oh no, not that. It's a great talk, and I understand the problem you're trying to solve. My concern with it, though, is it overly complex to the point where you need observability on your observability stack.
Right. Yeah, so that's a good point, and I think that's one of the concerns that people raise about open telemetry collectors as well. I think what we have done right now is we have a simple out-of-band monitoring setup that we have, where we just run stock Prometheus to just monitor these components that are part of the planet scale installation. But I think we want to get to a point where we run a separate set of collectors where they monitor the collectors that are scraping along with the metric store installation itself. And you have maybe the only difference is that the metric stores that are serving the end users are on the latest, greatest version, but the out-of-band one is one version behind to ensure stability. And that is what is being used to monitor the installation itself. So out-of-band monitoring is the key. Without out-of-band monitoring, I don't think any observability platform should be running, and this would be no different than that.
Hi. Okay, thank you. So yeah, we actually very well know the problems that you have. We had pretty similar problems in 2018, and we started building the same system. So we
very popular
actually,
folks.
yeah, we actually did it, and we open sourced it in 2019 under the name of Victoria Metrics.
Right.
And it's actually, we heard that it's very similar, including the multi-level cluster setup and everything else. But yeah, you can use it for free under the name of Victoria Metrics on GitHub. Yep.
Okay.
Do
And
you want to spell that for everyone?
Victoria Metrics. I used to joke as like Victoria's Secrets, but metrics, you know. Victoria. Yeah, like my
Victoria Metrics, yeah.
Victoria Metrics.
You didn't ask the question, actually. And the question was, did you consider using different or existing open source solutions for Prometheus scalability, like Thanos, M3DB, Victoria Metrics? And so
I think when we started, that was when, actually, let me correct it. So when we started, there weren't any clustered implementations of Prometheus that was available. So we just said that, okay, let's maybe build something ourselves. Towards the tail end of the centralized platform that we talked about, and it was ready to go live, that was when I think Cortex came out as pre-production alpha. So at that time, the risk was pretty high for us to say, okay, let's backtrack and then maybe go fully on open source. But like I mentioned, we use Thanos internally for the long-term store. And our query APIs are intelligent enough to figure out if a query should go through the Thanos query server to get the data from the object store, or just use the metric store shards that are running with the Prometheus storage engine. So Thanos is something that we use even now.
Thank you. How much data duplication do you end up in the zones versus the leafs?
No, there is no duplication at all.
Did copies from the leaf into the zone then, or?
No. So
Or it doesn't store the data in the TSB?
We store, depending on the criticality of data, either 2 or 3 copies within the same tier itself.
Okay.
But when you hop onto the tier that's higher, it's only rolled up data. So if you have a recording rule that say sheds pod node and things like that, only that recorded information goes into the zone. So identical data does not hop between the zones.
Okay.
Hi, Vijay. So can you tell me a little bit, you mentioned that, you decided not to use the Prometheus remote write addition to the latest version of Prometheus, and instead wrote a more custom,
Right.
lean gRPC
Right.
implementation.
Right.
Can you talk a bit about the implementation and the performance gains?
So to clarify, the internal API is used only between the leaf to the zone and then the zone to the root. From an end user perspective, it's all remote read and remote write. So
Okay.
we did not change that. The reason that we did this was to facilitate query projection, query pushdown on the query side, and to cut down the amount of data that's going through the remote from remote write into the leaf zone and whatnot. So if you have seen how Apache Arrow works, I think that's something that OpenTelemetry is also
Yes.
trying to look at.
Yep.
Arrow also has the concept of using a symbol table to encode the entire payload. So without using Arrow, we ended up writing something similar.
I see.
That basically does encoding to save on the bandwidth, basically. Is there a good reason to do it on the query side? Like, I wish my lead engineer was here. He would have a better answer for that, but I can definitely get back to you on that one.
Sure, yeah, that would be helpful, because, I mean, so did you still utilize the, between the communication between the leaf, the nodes and the root, did you still, the zone and the root, did you still communicate internally through just gRPC?
Yes, yes,
Okay.
yes.
So it was just
Yeah,
a
yeah.
socket?
Yeah, in root querier to zone to leaf querier uses gRPC. Index server from the leaf to the zone to the root uses gRPC. And our ingester to the TSDB also uses gRPC.
Okay, cool, cool, awesome, thank you.
But the OpenTelemetry collector to the ingester is remote write. End user query to the querier is the standard Prometheus HTTP APIs that are there.
I just had one question, just out of curiosity. What kind of work load was it on a man-hours basis? How long was the project? And
I actually cannot talk about that. I don't have the approvals to do that. Sorry.
okie doke. Okay, anyone else? Well, thank you very much, Vijay.
Thank you so much. Thank